So we were looking at the mass of a plane region. And so we just have this mass here, and there are different locations where there's a nice piece of dense material. So we can say the moment about the x-axis, we look at the distance any point is away from the x-axis, and then its desire to rotate about the x-axis, its distance from the x-axis is its value y. So that's why the moment, the total moment about the x-axis is to sum up all the MKs and their distance from the x-axis. Then the moment about the y-axis is my, and it is to sum up all the points, look at their mass and their distance from the x-axis, because if I want to see what its moment or its desire to rotate around the y-axis, I am looking at its distance from the y-axis, and that is its x value. Okay, so then in order to find the centroid, so in order to find the centroid, well, the centroid now, or the center of mass, has two components. So its two components are x bar and y bar, where x bar takes the y moment about divided by the mass, and the y bar takes the x moment and divides by the mass. Okay, so this is actually not very difficult. Let's say I give you an example. So I have a plane region with the following masses. So I have M1 equal to 4 at the point -2, 2. I have M2 equal to 3 at the point 1, 3. I have M3 equal to 5 at the point 2, -4. And I have M4 equal to 1 at the point -3, -2. Yeah. Okay. So now I have these different masses at these locations. So wherever my plane region looks like, you don't have to draw it, but I'm going to draw it. So I have a mass of 4 at -2, 2. So I have a mass of 4 here. I have a mass of 3 at 1, 3. I have a mass of 5 at 2, -4. And I have a mass at 1 at -3, -2. So the question is, what's the center of mass of those points? Okay, so compute the center of mass. Well, the first thing I have to do is compute the total mass. So the total mass is 4 plus 3 plus 5 plus 1. That's 14. No, it's not. That's 7 and 8. 7 and 6, that's 13. Help me. Okay, so that's the total mass. And then I need to compute mx, that's the sum, k equal 1 to 4 of mk times yk. So the first mass is 4, and its y value is 2. Actually, we're going to do just the easy way again, where it does it automatically for me. I likes this. Okay, so the first mass is 4, and its y value is 2. Then the second mass is 3, and its y value is 3. Then the third mass is 5, and its y value is -4. And the fourth mass is 1, and its y value is -2. So that comes out to be -2. Okay. Then we need to compute my. Yes.
So you did 5 times -4, and
I
then you
did 4. I did 4 times. I did 4 times 2.
4 times 2 plus 3 times 3 plus
3
5
times
times -4.
3,
So
that's
did you
5
want it
times
to multiply,
-4. And
Professor?
then, what's that? Oh, I forgot a 1, didn't I? I forgot a plus sign, didn't I?
Yeah, that's what I was asking.
Oh, thank you. It must have thought it was something else. -5. Thank you for catching that. Okay. All right. Then the next sum is the sum k equal 1 to 4 of mk times xk. And let's do this right this time. So I'm going to get 4 times -2 plus 3 times -1 plus 5 times 2 plus 1 times -3. And that is -4. Okay. So therefore my x
I
bar,
think that is it supposed to be 3 times just regular 1?
let me
Like-
see, 3 times regular 1, 5 times, y'all, I tell you, I ain't gonna make no excuses, but I'll be honest with y'all. My doctor keeps saying you need to reschedule a new eye appointment because I can't see. Two, stuff has to be big for me. Okay, so X bar is my over m. So that is 2 over 13. And Y bar is mx over 13. And so that is -5 over 13. Okay, so that's how you find the mass of a simple plane region like that. All right. Okay, so now let's look at a mass of a thin plate. All right, so that was mass of a plane region, mass of a thin plate. Okay, so for the center of mass of a thin plate, all right, Actually, I'm going to go on to the mass of a lamina because that's where I really want to be. Okay, so what's a lamina? A lamina is just a plane region. And when I say plane, I mean flat or region in the plane. So I have something that looks like this. So I take something that looks like that and I want to draw and try to figure out what the mass looks like. So I'm going to take, and here's underneath some curve. So this right here is y is equal to f of x. Okay, and I want to find the mass of this region. Okay, so as we said before, so this whole region is what I'm trying to find out. This is my region R inside. Okay, so we said M is the mass. And as we said before, we just summed up all the little pieces. All the little pieces of mass, delta MK. Well, now we're in 2 dimensions. So now density is equal to mass per unit area. So therefore, our little piece of mass is now going to be our density times our little piece of area, wherever that is. So my little piece of area, okay? But when I'm trying to do this, whatever, so let's take a little slice now. So I'm going to do my little slice here. So here's my little slice. That's just this little piece right here I'm looking at. And if I'm looking at this piece and I'm trying to determine what the, hello? I'm trying to determine what the area of this piece is, then I'm going to have this length, that's delta xk. And then if I take some small x in the middle and find this height, f of xk, and take it, I can find that the area of that little slice is simply to take the function at some xk and multiply by the width of that little piece. Okay, so now I get that delta M, my little mass piece, is equal to delta of x times my area, which is F, this is MK, times delta of xk times my F at xk times my delta x. Okay, so that's what I get, that little piece. So now when I sum up all of these, so now I'm going to get my mass, again, is approximately my sum. This should be approximate because I'm not talking about exact. I'll make it approximate, okay. Of my delta MKs. This is the sum, K equals 1 to N of delta of xk times F of xk times triangle delta of xk. So if I sum all those, I get an approximate value for the mass. Okay, so now we're going to let the delta xk's go to 0 and n go to infinity. So therefore I get my mass becomes the limit as n goes to infinity of the sum k equals 1 to n of delta of xk f of xk times delta triangle of xk. But again, this is calculus. The limit of a sum is an integral. So therefore I get my mass turns out to be the integral from a to b of delta of x f of x dx. So now I have a formula for my mass. Okay, so now what I need, so we have a formula for the mass. That's actually fairly easy.
Professor,
Yes,
sorry, just one more question. So you said the limit, so you changed the limit to when n reaches infinity times the sum. How would you read that? The sum of.
okay, so if you remember, this is Riemann sums. This is an old topic.
I was just how would you say that? Like the
Okay,
sum of.
So the Riemann sum, okay, so you have a partition. I'm gonna do it quickly. I have this area. I have this, whoa, that's not what I want. Okay, so I have some function. Remember we did the area under the curve? Has some function, looks like this. And then I split it up into partitions. So I split it up into intervals like this. And then we found the area of each individual piece using trapezoidal rule or something like that. So we found these areas like this. And that gave us an approximation to the area under the curve. So any one of these, that little area, all right, over xk is simply f of x, some f of xk times delta xk. Now, every time I let this get smaller, when I go to a smaller, when they get smaller, like this, so now I've doubled n and the approximation gets better. Now let's quadruple n. So now my little rectangles are really small. So as I let n, being the number of rectangles I have, go to infinity, that gives me the actual integral under the curve. So that's what I was saying. Anytime you take the limit as n goes to infinity of the sum k equal 1 to n of whatever you have. So in my case, whatever it is over here, f, let's say f of xk dx, let's say, nope, not dx, it's delta x. This thing becomes, I don't want it there. This thing becomes the integral from wherever you start to end, a to b, of f of x dx. So that's how we defined the actual definite integral in Calc 1. So whenever I teach Calc 1, I always say, let me teach Calc 2. Who was your Calc 1 teacher? Because your Calc 1 teacher should make it very clear that this when you take the limit of the sum of partitions of areas, you get the integral. So the limit as n approaches infinity of the sum of k equals 1 to n of whatever comes next is the integral of that thing. And delta xk becomes your differential. And then f of x k becomes your function. Diarra.
That helps out a lot. Thank you.
Do you, it's kind of a little fuzzy, but that helps a
No,
bit.
no, it made a lot of sense. Thank you.
Okay, you're welcome. Okay, all right. So now we need to define the moment dmx about the x-axis. Okay, so the moment about the x-axis is the same way as it was before. All right, we're assuming the distance from any point to the y-axis, well, to the x-axis, its distance is yk. So therefore, mx is going to be approximately the sum k equal 1 to n of the distance yk times the little mass element. So then this becomes the sum k equal 1 to n of yk, and delta mk is f, no it's not, it's delta of xk, f of xk dx. So therefore, when I do m of x, it is the limit as n approaches infinity of the sum of k equal 1 to n of yk delta of xk times f of xk dx. So therefore I get mx. This becomes the integral from a to b of y delta of x, f of x dx. And I can do the same thing to get my. So my similarly my is the integral from a to b of x delta of x, f of x dx. And so then, now that I have everything, I now know what x bar and y bar are. Did I circle the wrong thing? What did I just do? Well, I think I hit, yeah, I hit the wrong thing. Okay, so therefore the center of mass again is x bar is equal to my over m, and y bar is equal to mx over m. Okay. Something is not right. The first one is not right. The first one is not right. mx is not correct. MX is not correct. Let me go back and fix that. That is not correct. So bear with me. We're going to do the moment about the y-axis first. So I'm going to change these to y's. Just bear with me. And the reason why I realize this is not correct is because not correct in my notes. Okay. That is not right. I know this is, just bear with me. That's not right. I need to look at the pictures to do this thing. And so let's look at the pictures. Okay. The moment about the y-axis, again, where's my picture? I'm going to take this same picture and pluck it because I need it for y'all to see. Okay, because that derivation was wrong. And when I was doing it, I was like, something's not right. Okay, so let's assume if I choose to concentrate my mass right here, then the distance this thing is from the x-axis is just x. So wherever that is, that distance from the y-axis is just x.
How do you know that, Professor?
So if I take a point, this point right here is xk, yk.
Oh, I forgot about that.
Okay, so the distance it is away is just xk. Okay, and again, its desire is to rotate about the y-axis. That's its desire to do that. All right, that's the torque that causes it to want to rotate about the y-axis. Okay, so therefore the moment about the y-axis is my. I knew something was wrong. I'm like, this don't look right. The sum, and this should say my, is the sum k equal 1 to n. The distance it is, which is xk times delta mk. But this is the sum k equals 1 to n of xk times delta at xk times f at xk delta x. Okay. All right. So therefore my is the limit as n approaches infinity of the sum of k equal 1 to n of xk delta of xk f of xk triangle delta of xk. But this puppy becomes an integral. So I get my is the integral from a to b of x delta of x f of x dx. So that is the moment. So that one is correct. It's the other one that was wrong. This one is right. The moment about the y-axis is correct. The one that's wrong was the moment about the x-axis. Okay. So let me.
Would that go for the moment of the x-axis?
Yes, this is the moment about the y-axis, my. That is its desire to rotate. See my circle, De'Ara?
Yes.
See my blue circle here is the desire for it to want to rotate about the y-axis. And it is, go ahead.
So what I was saying was like for the moment of x about the x-axis. So would that all that you did for the my, can I do that for the mx? Does that make sense?
Yes, but, and see, that's what I just did, but see, it's tricky. So that's why I was going to say, let me show you what I just did was correct,
Okay.
but it's difficult to do it that way. So I'm going to show you, this is the way, because you can't always figure out. Notice how I concentrated the mass right here. I do know that the mass is inside that strip, okay? And that mass, no matter where I put it inside that strip, it is always going to be X distance from the y-axis. You understand that? No
Yes.
matter, if I put that dot here, it's still the same distance from the x-axis, the y-axis. If I put that dot here, it's still the same distance from the y-axis. So the distance from the y-axis is always xk if it's inside that strip. Now what happens with the y one is the y one, that's the hard one, okay? So here's the y one. So the moment about the x-axis is the hard one. Okay, so the moment about the x-axis, same picture. Okay, so I got my picture back. So now the question is, where is the mass? So I already know that no matter what I do, the mass is in that strip, and it's always a distance of x from the y-axis. What I don't know is how far that mass is away from the x-axis, because now when I want to do the moment about the x-axis, I want to look at its desire to rotate that way. So its desire to rotate that way is dependent on its where it is inside, that's a bad color, where it is inside here. So each one of these has a different YK. Back here, everything had the same XK. It was always the same distance from the y-axis. But here, each one of these has a different distance from the x-axis, and that can make it hard. So what we do instead is we take the distance, the YK distance. So we're going to use the YK distance. So we still get the same thing. So now we get the MX is approximately the sum K equal 1 to n, almost said infinity. Ooh, that's a bad one. K equals 1 to n of the YK distance, again, times delta MK. And this is the sum K equal 1 to n of YK times delta of XK, F of XK, triangle delta of XK. But we don't know YK. YK can change. So since YK is variable, we're going to define YK to be the average of F of XK. So in other words, since I don't know where YK is, I'm going to make YK be half away of FK. I'm not going to, so now I'm just saying, you know what? I'm not fooling with this. I'm just going to say it's going to be there. And so we define YK to be 1/2 of F of XK. So it is the same integral I just did. Now I'm explaining it better. Okay, so therefore we get MX is approximately the sum k equal 1 to n of yk, which is 1/2 of f of xk, delta of xk times f of xk, delta x, k. And so therefore mx is the limit as n goes to infinity of the sum k equals 1 to n of 1/2. And now I have f of xk, and f of xk gives me f of xk squared delta of xk. I should have put that in front. I normally do, delta xk. So therefore mx is the integral from a to b of 1/2 delta of xk, delta of x, f of x squared dx. Okay. So I should have done them in that order, and then it's now clear. Okay. And now I can say the center of mass. Which is x bar. Y bar is x bar equal to my over m, and y bar equal to mx over m, just like we said. Okay. Woo-wee. All right. So here is a problem. Find the center of mass of a plane region covering of center of mass, I'm sorry, of a thin plate covering the plane region bounded by the parabola. I'll write the parabola in. The parabola, for those of you who are writing now, is y is equal to 4 minus x squared and the x-axis, whose density is 2x squared. Okay, so here we go. So we have a plane region. It's got a thin plate over top of it, and we're trying to find the mass of it. So y is equal to 4 minus x squared. And the density is delta is equal to 2x squared. Okay, this is the most basic of easy of wonderful kinds of problems. Okay, it is a parabola, so it's an upside down parabola. Okay, it looks like this. So this is the region, and we need to find its center of mass. Now notice it is gets really dense on the sides. Okay, almost super infinitely thin in the middle, but very dense on the sides. Okay, so we need to find the center of mass. Now, this is actually a fairly easy problem to find the center of mass because this thing is symmetric. So this region R is symmetric. And its density is symmetric. So it's the same shape and its density is symmetric. So therefore, I expect the X bar coordinate of the center of mass to equal 0. In other words, it should balance perfectly like this. What I need to find is where this point goes. So I kind of know it's going to be somewhere, but where is the center of mass? Now, I don't expect it would be up here because it's heavier down there. So I expect that my center of mass, the Y value is going to be down here where it's thicker or wider. And so we need to find that point, okay? So the first thing we need to find is the mass. Okay, so M is the mass. And that is the integral from A to B. Uh-oh, what are A and B? Got to figure them out, okay? Integral of A and B of delta of X times F of X dx. So that is the integral of the mass. Okay, what is this point? Can anybody tell me what this point is right here? And what this point is right here? Anybody tell me what those are?
Is it 4? Negative 4 and 4?
Almost. How'd you get negative 4 and 4?
From the equation. 4
And
is,
what did you do?
well, I kind of guessed, I'll be honest.
Okay, well, when X is 0, Y is 4. So that height is 4.
Okay.
So now what happens when Y is 0? Y is 0 down here, right? So when Y is equal to 0, I get 4 minus X squared is equal to 0. Ah, what is X?
Positive and negative 2.
Okay, so my X's are positive and negative 2. All right, so there actually is a way to determine those. So I know A and B now. So this is the integral from negative 2 to positive 2. Delta is 2x squared. F of X is 4 minus X squared dx. And that integral turns out to be, let me see, what's my mass? 256 over 15. Okay, so now we know the mass. All right, remember I said one of them is always easier to find.
Wait, Professor.
So, yes.
I don't want to ask a dumb question, but I just want to make sure. So how did you get your answer?
Okay, how did I get the formula? Or how did I get this answer? Okay, all right, so I multiplied everything out. and integrate it and evaluate it. So the step between that, I said this is the integral from -2 to 2. I got 4x squared. I'm sorry, no, I didn't. I got 8x squared minus 2x to the 4th dx. So then that gave me 8/3 x cubed minus 2/5 x to the 5th, evaluated from -2 to 2. And that gave me 256 over 15. Okay.
Yeah, you good, Professor.
Okay. All right. The next easiest one to find, well, let's see. What was the easiest one? Doesn't really matter. My, in order to find x bar, we need my. So let's find my. And that is the integral from a to b of x delta of x, f of x dx, integral from -2 to 2 of x, delta of x is 2x squared, f of x is 4 minus x squared, dx. And that comes out to be, what am I doing? My? My comes out to be, you're gonna be like, what in the? That comes out to be 0. Okay, and then we now need to compute mx. So that's the integral from a to b of delta of x times f of x squared. I forgot my 1/2, I need that, dx. So that's 1/2, the integral from -2 to 2, delta of x is 2x squared times 4 minus x squared dx. And that comes out to be 2048 over 105. Okay. So there it is, this integral. So x bar is my over m. So that is 0. That checks out with exactly what we thought we would get. And y bar turns out to be 2048 divided by 105. And then we're going to divide that by 256 over 15, or multiply that by 15 over 256. And that turns out to be 8 over 7. So therefore, my center of mass just turns out to be 0, 8 over 7. Okay. All of these problems are like this. Okay. Any questions?
So Dr. Locke, all we have to remember the difference for my versus my versus mx. The
Yes,
mx always have the half, right?
Say that again.
So for this, the
My has an x, mx has a y. But we got to remember that the y we took was the average value. So that's why mx turns out to be 1/2 f of x squared. Yes.
Oh, okay.
Okay. Of course, I got to make it just a wee bit tougher. All right. So now let's suppose for a moment we want the center of mass or the centroid of a region between two curves. Okay. So now the region I want looks like this. There's one curve. Here's another curve. Okay, A, whoops, make that dark. A and B. Okay, so here's my region now. So my region is this area in between. So this is my region. It's the area between these two curves. And I want to find the center of mass. Okay. All right, so I want to do the same thing we did before. And that is, I want to grab a small chunk, a small section right here. All right. And there's my mass. So I'm looking over at this particular region. All right. Well, I know that in order to do the center of this mass, I have to think about where this thing is. So the one that's the easiest, again, is MY. MY is easy because MY basically is going to look at the difference between, in my, here, where my curve is, whatever my area is of this piece. So whatever my area is of this piece, its distance is still always X away from the Y-axis. So if I want to rotate that region around the Y-axis, it's still going to be a distance there. The thing is, what's the area of that little piece? Well, you got to remember now the area of that little piece is going to be the top function. Let's take this as F2, F of X, and the bottom function as G of X. So the area of that little piece is to take the top height, F of XK, subtract the bottom height, G of XK, and multiply that by delta X. Okay. So therefore, when I go to find the mass, my delta M is delta of XK times A of XK. So that's just F of XK minus G of XK times delta of XK. So therefore, when I go to compute my mass, I'm gonna skip the limit and the integral stuff. I'm just gonna get the integral from A to B of delta of x times f of x minus g of x dx. So when I'm looking at the mass between two regions, okay, so that's the mass of the area between the two regions. And then I can find my. My is going to be the integral from A to B of x times delta of x times f of x minus g of x dx. So that's going to be my my. Okay, once again, mx is difficult. All right. So the reason why mx is difficult is because now I got to take this same picture and I have to figure out how far this thing is from the x-axis. So I got to figure out that distance. So now in order to, it's again still yk, so I'm still going to get that my mx is approximate the sum k equal 1 to infinity of yk times delta of xk times f of x minus g of x dx, because that part is the area, so that doesn't change. But therefore, we have to figure out what are we doing with yk again. So this time, we're going to let yk be the distance halfway between f of x and g of x. So it's the distance between them. So if you add them up and divide by 2, that is the average distance between f and g. So now I get that my mx is approximately the sum k equal 1 to n. Yk is 1/2 f of xk plus g of x. And then my mass is delta of xk. These should be k's. Those should have been k's, k's, k's. And that's wrong. That should have never been dx. That should have been delta xk. And this now is f of xk minus g of xk times delta xk. So skipping all the particulars, I get mx becomes approximately the sum k equals 1 to n. I get 1/2. And if I take f of xk plus g of xk times f of xk minus g of xk, and I FOIL that, I get delta of xk times f of xk squared minus g of xk squared delta of xk. So skipping all the limit stuff, I get mx turns out to be 1/2 the integral from a to b of delta of x times f of x squared minus g of x squared dx. And for this region, same thing. Again, the centroid x bar y bar is equal to my over m and mx. Okay. How much time do I have? 7 minutes. I can do that. Find the center of mass of a thin plate over the plane region bounded by the curves y is equal to x over 2. Y is equal to x over 2. G of x, I apologize, is equal to x over 2, and f of x, which is equal to the square root of x on the interval 0, 1, whose density is x squared. Okay, so g of x, the bottom curve, is equal to x over 2. And f of x, the top curve, is the square root of x, and the density is x squared. Okay. I don't even need all that. I just need this. Okay, so f of x is equal to x squared is on the top, so that looks like this. I'm sorry. F of x equal to the square root of x is on top, and g of x is a line that looks like that. And interval 0, 1. Okay. So x is equal to 1 here. All right, so this is my region. Okay. So we have to compute the mass. The integral from a to b of delta of x times f of x minus g of x dx. Anybody want to take a stab at that very quickly to give me the formula for that?
So you would change it to x squared times square root of x subtracted by x over 2. You want me to change dx too?
No, it's just dx.
Okay.
I need limits of integration.
So then this limits of integration would be 0 to 1.
0 to 1. Okay, good. And my and mx, I'm going to let you guys calculate. And I'm going to go ahead and take attendance.